get you engaged a bit, I brought you a puzzle directly in the first slide of this talk. And this is a line of Java code, if you want. Could be other language as well. And first question to you is, where would this line of code be used? What kind of algorithm? There's too many. Louder? Binary search, yes, correct. You know, I gave this talk at the Java conference 2 months ago, and there were just crickets. Like, no one was saying anything. But this is good, this is good. This is a much better conference, but much better crowd here. Yes, binary search. Now, second question, what's wrong with that line of code? Sorry?
There was a bug in it for 20 years.
In binary search? But what specifically, what's wrong with this line? Overflow, yeah, this is a very good crowd. I've had people sitting there for 2 minutes not saying anything. Yes, and this has been known for a while that this is a problematic line of code, yet we keep teaching that in any kind of computer science curriculum. And this guy, Joshua Bloch, he has written about it in 2006. So it's been known for a while that this is a problem. Now, the thing is that when you're just writing unit test cases, you would probably not encounter that problem, right? So it would be very hard to find that sort of problem if you're just like enumerating test cases, because in order to trigger that kind of problem, in an actual binary search routine, you would need to supply a very, very long array for that problem to happen in the first place. Okay, so we've completed the first puzzler. I have another puzzler for you, and I'm showing you a picture now from a conference in Oslo, and I want to know about you what the how the people are arranged in that picture. Yes, based on beard size. So one of those is me, and the other people are also people from the Scala community. So I'm not sure who of you have been to FlatMap in Oslo. It's been a while ago. Yes, so those people are ordered by beard size, and if you were to write that in Java, we could write something similar like that. We could call the sort function, and we could specify a predicate saying that we're comparing the beard size of one person to another person's beard size. Now, unfortunately, if you're running that on every human on Earth, you would get that kind of error. You would get an array index out of bounds exception in Java, which is kind of unsettling if you think about it. Why is there an array index out of bound exception somewhere in the comparable timsort class? Like, what is the comparable timsort class in the first place? Why is it throwing some exceptions to me? And it turns out that this was also broken for a very long time. And you could think that the sorting routines in the JDK have been tested excessively, yet this bug has remained there for a long time. And there was this paper from a conference in 2015, OpenJDK's collection.sort is broken, the good, the bad, and the worst case. And there it was also a problem. I'm not sure if it was actually based on an overflow. I think it was someone trying to be very clever about finding pre-sorted segments in the array and then doing some fancy tricks that failed. Now, this is yet another example of when testing just doesn't cut it, because arguably JDK is very well tested, but the researchers who wrote that paper, they had to resort to using formal methods in order to uncover that problem. All right, so now let's talk about bugs. Let's talk about how bugs appear and how we deal with bugs. Now imagine a typical software development workflow. We would typically start by writing down the requirements of what we want to do. In the case of the collections.sort, the requirement would be, I'm giving you an array and I want the array sorted. So that's not so complicated, right? Then we're somehow designing it, or if we're designing a large program, we would call it architecture. So in JDK example, they would have settled on the timsort sorting routine, which I think is a derivative of merge sort. Then they sit down to actually implement it, and then they write some test cases, and then it's being operated somewhere in production. Now this is kind of like a waterfall model. If you want to make it agile, just add some loops there, and then you have the agile development workflow. But generally speaking, that's the way we do things. And one of the issues how bugs are how bugs keep reappearing is that we just focus our attention during programming mostly on those last 3 stages regarding implementation, testing, and operation. And this is what we call debugging, right? So we would find some bugs, for example, during testing, or we might have some sophisticated runtime monitoring, A/B testing, whatnot. And we rarely think about how bugs could actually even arrive or could manifest themselves somewhere early in the process. Now, don't get me wrong, this is not bad per se, right? There's a paper from 2014 that says simple testing can prevent most critical failures. So it turns out that if we were even doing testing correctly, we would have a lot fewer problems in our day-to-day lives. And I also have a talk on property testing and other testing methods. So this is all good. I don't want to deride testing in this talk. But there's this obscure professor by the name of Edgar Dijkstra who has said this quote: "Program testing can be a very effective way to show the presence of bugs, but it is hopelessly inadequate for showing their absence," right? So if you're writing your program in VS Code or in IntelliJ or whatever, and you click on the run tests button and they're all green, you don't know anything really. You just know that for those particular things that you have tested out, it all seems to be working fine. But you can't be sure about all the other cases that you have not bothered to write down, or that the property testing framework has not bothered to generate. Right. So I think up at this point, I may have convinced you already that testing is somewhat inadequate in some scenarios. And I could sell you now the antidote to that, but I'm not selling anything, so I'm just telling you about it, and if you want to buy it or not, that's your choice. And the antidote would be formal methods. Now, before I started, I already had a show of hands who has heard of Isabelle and TLA+, and many people have heard about it, but formal methods is a lot more than that. There's this definition from Cesar Munoz from NASA, the American Space Agency, and he defines it as formal methods refers to mathematically rigorous techniques and tools for the specification, design, and verification of software and hardware systems. Now, this quote is remarkable in many ways. So, the first way in which this is remarkable is that NASA, for example, runs a dedicated formal methods academic conference. So they're very invested in that sort of thing. But also, what I find remarkable is that it includes not just the verification, but also the specification design aspects of systems. So it's not the case that formal methods you can only use on existing systems, and you may have some tools to analyze your Java code or your Go code or your whatever code, but you can also use those methods to actually design your system, right? And even just writing your specification might already uncover a lot of problems that you may have only caught later on. Now, again, in the show of hands, only one person raised their hand saying they've used Isabelle or TLA Plus before, but I'm going out on a limb and I'm going to claim that you have already used formal methods, and maybe even without knowing it. And I have 2 examples for this. So the first example is a silly example, and the second example is a real example. Let's start with the silly example. Flowcharts. While doing the research for this talk, I realized that flowcharts are ISO specified, and you can actually buy those kind of templates to make like pen and paper flowcharts. And I was speaking to a friend about this, and then he said, "Wait a second, I still have one of those at home." So those things were really produced and sold in order to make flowcharts. Now, the cool thing about flowcharts is that everybody can interpret them, right? They're just boxes and arrows. But one thing that I learned in research for this talk is that it's actually really formally specified what those boxes and arrows mean. So if you shell out some money to ISO and download the specification document, or just find it on Google Images, you will find detailed description of all the shapes that you have in the flowcharts. And the cool thing is that you have a syntax. Now, those syntax is kind of graphical boxes, and you have a semantics. Now, I don't want to go into detail of how the flowcharts are defined. I think we agree on the fact that flowcharts are kind of easy to read. So you just start from the top and then you follow some decisions. So it's very easy to communicate your intent with that. And they also qualify as a formal method because they have some kind of specified meaning. So that was the silly example. And now I have a serious example, and that is type systems. So type systems can also be seen as one particular kind of formal methods. And this serves to illustrate another point, right? So a type system does not necessarily tell you about anything about the semantics of your program. It just tells you about things that cannot happen in your program. So this is just some screenshot from a TypeScript type error where it tells you that somehow string is not compatible with string or number. So it tells you, oh, well, if there is a number, then it somehow doesn't work. But the cool thing here is that type systems are very lightweight. So they are included in your compiler, and they're being run every time you type something or when you compile it, as opposed to flowcharts, which exist in a separate reality to your program, right? You cannot compile a flowchart down to x86 bytecode, this is different for TypeScript or other type system language. You can compile them and actually run the thing. Right, so this basically just serves to illustrate the point that formal methods are quite diverse. So there's a whole lot of different techniques, and there's no reason to be scared of them. And a friend of mine, Hillel Wayne, he has written extensively on his blog on different lightweight formal methods, so he also recommends to just draw a state machine if you're unsure about the state of your system. Just draw a state machine, and that's already better than not having a state machine. Or maybe something simple like Boolean decision tables. So you just write a big table of all the different inputs of your system and how it should behave, right? So this would be something like a formal method already. Right. But the main point of this talk is not about those lightweight formal methods. They're cool, you can use them. My talk will be more about formal verification. And to set the stage, the idea with formal verification is that you have a specification in some language, and you have some implementation in maybe the same language or in another language, and then you have a proof that connects that the implementation actually satisfies the specification. And if we go back to the binary search example, I will show you what that would look like. This is the same line of code, line of code that has a problem, but we're trying to model it formally anyway. So we first need to specify what we would require from the inputs, and then we would specify what we expect from the outputs. And in this case, we would, maybe in Java syntax, we would add some assertions. So we say in the binary search example, the low index must be less than the high index, and the low index must be greater than 0. And the output is then expected to be somewhere between low and high, right? I mean, there's still a bug here, but I just wanted to show you what that would look like. So these two parts, above and below the assertions, they are the specification, and then in the middle you have the implementation. And then the proof somehow needs to come from that to show that it actually holds, or in this case, produce a counterexample if you have the integer overflow. And this is the way you could do it with Java-based tools. So there are tools for Java that can interpret those assertions and then try to make some proofs about it. But there's also other ways of doing things where we abstract away a bit from the programming language. So I basically tried to put that now into a formula. So a mathematical formula with quantifiers and implications and everything. And there we would say, well, we have some low and high variable that are coming from the integer 32 range, because we're talking about machine integers here. You also have the preconditions on the left side of the implication arrow, and then you want to know that low is less than or equal to the computed midpoint. And in order to make it abundantly clear that there is a problem waiting here, I used a plus 32 to indicate that you have an addition with overflow here going on. Right, so this is, of course, something you could write on paper, but that's nothing that helps you in your daily programming life. Now let's basically look at what we're doing in practice here. And before I explain to you what we're doing in practice, I have yet another puzzle because I want to explain to you what the product is that we're building. So I have 4 pictures here. Top left is shells, the bottom left is salt, and then you have gold and banknotes. I think that should be easy to see. So what's the common thing among those pictures? Payment methods, yes. Or even some would even go as far as calling them currencies, right? And right now, so I'm from Germany. Right now we are at the bottom right. We love cash. We love physical cash. We love physical banknotes. But I don't think I have to explain to you that there's a 5th step happening now, the evolution where we're going to digital currency. Now, the topic of digital currency is always a bit fraught because many different people interpret many different things in it. We're not building something like Bitcoin. We're not building a blockchain. What we're doing is called central bank digital currency. So central bank digital currency is basically digitized cash in the sense that it's a payment method that's issued by the central bank, so it works like cash and it can be anonymous and whatever, but it can also be used both online and offline, which is something that you cannot use cash online. And on the other side, bank deposits and so on, they're not guaranteed by the central bank. So CBDC tries to bridge the gap between those two things. And as is typical with these kinds of payment methods, they're usually used by central banks, commercial banks, or some kind of payment service providers, so PayPal and whatnot. Now, what's peculiar about those customers is they typically don't like if they lose money on something. And also their customers don't like if they lose money on something, right? So if there's a transaction that somehow gets aborted and cannot be retried or cannot be rolled back and the money would get lost, that is a problem, generally speaking. So they have quite some interest in having bulletproof software where these problems cannot happen. And I mean, they have happened in the past, right? So if you look at, this is just from the last few years, there have been numerous such problems. And what's good about the existing banking systems is that most of these problems can be fixed at some point, right? So I'm not sure here who has been affected from these UK duplicate payments at some point, where some people woke up to have like a large negative balance on their account and they couldn't pay their bills anymore. This got fixed after a few days, but within those few days it was a real problem. Right, so we try to not run into the same issues, and we're using formal methods to avoid that from happening. Now, as opposed to a traditional bank account where you have a balance that's somewhere stored in an account in a database, we have a different way of representing the money. Now, if you're familiar with cryptocurrencies or with Bitcoin or something like that, it will be quite similar to that. How we represent money is by attaching some kind of denomination to a cryptographic key pair. So in this case, it would be 20 euro that is attached to some kind of elliptic curve key. But the details don't really matter. What matters is that you can manipulate those tokens. So they somehow get passed through the system, so I can give that 20 euro money to someone else, but I can also split it into smaller bits or merge two small tokens into a big token. And we can represent it abstractly and model the flow of these tokens through the system. So this is one example flow. Initially, the central bank needs to be creating the token out of thin air because the central bank is typically the only authority that is allowed to create this money. So we have here kind of a create operation, and after that create operation, 10 euro or dollar or whatever just exists, right? So they have the power to do that. And then they can put it into circulation, and then a user could, for example, say, well, actually I need 2 euro now, and I will keep the remaining 8 euro for change, so the user can issue this kind of split and do with the result whatever they want. And conversely, they could also do that with 2 smaller tokens and merge them together. Now, obviously, this is not something that the random user would do directly, but instead they would be relying on some kind of wallet software or hardware to be doing those operations for them. And for good reasons, they would need to trust that those wallets are implemented correctly. Right. So does it remind you, does that representation remind someone of something? So if you look at that, you think like, what is the mathematical concept that could model that sort of thing? Sorry? Shells? What are shells? Monoid, yeah. More ideas? I was hoping for someone to say graph, but okay. There's definitely some monoidal properties for that also hidden somewhere there. Anyway, this is very abstract, right? So this has nothing to do with the concrete implementation. So as this weird Greek guy said, it's kind of like in this abstract realm of ideas. These objects, they are somewhere floating around and we can describe them. But yeah, this has nothing to do yet with the implementation. So we need to go a bit further down from the specification to the implementation. If you remember the slide, this is the ideal way that I explained to you how verification works. We have the specification, which in our case would be some kind of graph-based model. And then we need to drill down to the implementation. But in reality, there are more intermediate steps when you do formal verification. So in reality, you would split off the specification into multiple parts. Here I just have two parts. The abstract specification, where we talk, for example, about sets, and some sums of sets and operations on these sets. Then executable specification would be, for example, saying, well, we don't really have sets, real mathematical sets in programming languages, so we need to implement those things with lists. Because sets in mathematics can be potentially infinite, and we don't have a way to represent that. Typical verification projects have a whole lot more different of those steps. So you would start out by saying, well, we want to represent those sets as lists, or maybe you want to represent them as red-black trees, and then you would need to come up with an ordering of those things. So you have these multiple intermediate steps before you then actually end up at a concrete implementation that might be in Java or something like that. Now, fortunately for us, we are using a tool, which is called Isabelle, that can cover all of those. It can cover this entire range from specification to implementation. If you go to the Isabelle website, you will be greeted with that screenshot, and that screenshot is a demo implementation of normal linked lists, as you would be familiar with in Haskell or Scala or whatever. The way I think about Isabelle is that it's basically just a programming language. It's a bit of a weird programming language, a weird syntax, but it is basically a programming language that allows you to do some proofs about that as well. Or as my PhD advisor Tobias Nipko said, Isabelle equals functional programming plus logic. So you don't just do functional programming, but you also have some kind of mathematical logic. For those of you who might be familiar with other systems like Coq, Isabelle is based on set theory and not on type theory, but that is mainly just a technical distinction for now. You can ignore it if you don't know it. All right, so let's go back to this graph model. And I want to tell you now a bit more detail how some of those properties can be formalized actually in Isabelle. When you have this token passed around in the system, we can distinguish between two states of the token. The token can either be spent or it can be unspent. A token is spent if it's being used somewhere already, and it's unspent, well, if it's not being used. And in this case, the token that's worth 10 euro is spent because it's been used as an input for the splitting. However, the 2 and the 8 are unspent, because they're not yet assigned any further command of any further operation. Yes, someone asked about the UTXO model. It's comparable to that. It's not exactly the same thing, but you can think of it that way. Yeah. Right. So one of the first things we can define on this graph is we can define the balance of the graph, or alternatively, if you want to call it, the amount of money that's in circulation. Because the amount of money that's in circulation is basically just everything that's unspent as of now. So we can just define that in Isabelle. So I can say the graph balance, I'm defining it as a natural number, and it's the sum of all the value of all the unspent tokens in circulation. Right? So what's kind of interesting about Isabelle is that it has this functional programming syntax of like function name equals and then definition, but you can also mix in those mathematical symbols in there. And what's also cool is that this is actually operation on sets. So the unspent set, I didn't put the definition of the unspent set on the slide, but it's a mathematical set, and this is a unordered sum over this. So it doesn't force any order. So this is a very abstract way of specifying things. I'm not having to talk about iterating over lists or iterating over trees. It's just this very abstract notion of sets. Okay, so that's one thing. But we also want to prove something about it. And what we want to prove about it is that during normal operation of the system, so normal user operation, the amount of money in circulation does not change. So even if I'm doing operations on the tokens, if I'm splitting them, merging them, doing something like that, this amount of money should stay constant. Only if the central bank decides to create new money out of thin air, then the amount of money increases in circulation. Right, so one more definition I have to give for that before I can show you the dilemma statement. We can group those graphs into kind of subgraphs, and we can connect the tokens that are being consumed and the tokens that are being produced in a single operation. So here on this slide, I have two groups. So I have the C1, which is the creation of a token. It has no inputs, but it has one output. And the C2 is the red one, which consumes the token worth 10 and produces a token worth 2 and a token worth 8. And then we can define something on those boxes, and we would define the value difference of that thing. So for creation, the value difference would be 10, because now we have 10 euro more than we had before, whereas in the red box, the value difference would be 0, because we have exactly the same amount of money before and after. 10 equals 2 plus 8, so the value difference is 0. Okay, so now I can actually prove something. So I can prove a lemma that says the balance of the graph, the amount of money in circulation, is equal to all the value differences of all the token operations that I have carried out over the evolution of the system. So on the left-hand side, the graph balance was originally defined as the sum of all the unspent tokens. And now on the right-hand side, I'm talking about the value difference when I'm looking at each command. So I'm basically comparing the 2 and 8 that's here on the right side with all the things that have happened before. So I'm kind of trying to do even like an event sourcing approach where I'm following all the events that have happened in the system and then trying to show that the end result after applying all of these events is what I would expect. Now this is where the problem starts, because if you're familiar with how these cryptocurrencies work, that doesn't seem very surprising, this result. So I mean, someone said this looks like UTXO, it is like UTXO, yet to prove that is actually correct is a whole can of worms, and this is always the case in those verification projects. So you're pulling on one string and then you have like a whole theory that comes out of that. What I found out while trying to prove that is I first need to prove that the graph balance is actually positive, or well, non-zero basically, because the value difference can be negative. There are commands that actually withdraw money from circulation, but they can only withdraw something from circulation if it has existed before. So I cannot just go net negative in that scenario. So I need to prove kind of a helper lemma first that also shows that this value difference is always greater or equal to 0. And then I can start thinking about how to prove it actually. So I need to prove both things at the same time. This is something called simultaneous induction. And typically in math lectures, this is not being taught. It's just when you're starting to use those systems, you will just stumble on those things. Okay, I have to prove these two things at the same time somehow. Otherwise, it doesn't work. So I would argue and say that we have not yet figured out proof modularity. So sometimes you just have to prove two different things at the same time. Now, I'm already showing this on the slide that this is something that has to be proved by induction. And the cool thing about Isabelle is you can't I mean, you can do induction over natural numbers, over lists and these things, but you can also do custom induction. So you can define your own custom induction rules. So I have defined here an induction rule that goes over the graph structure because our graph is actually directed in acyclic. And it turns out you can define induction over directed acyclic graphs, which is something really interesting. And Isabel helps you even. When you write that template of a proof in the system, it will ask you, it looks like you're trying to do an induction. Do you want to have a template for that? And I'm not sure here who has flashbacks to high school, where you got drilled with the induction templates. So basically it will then list you can click on it and it will list you all the cases and then you can go on your way of proving things. So in this case you would have the base case which starts out with an empty graph, so you have no money, you have no circulation, you have nothing, in which case both of that would be 0 equals 0, trivial. And then you have the next case would be the steps, so depending on what kind of thing that you're doing, introducing a new token or modifying an existing token, that this is still satisfied. Right. So because of time, I actually cannot show you the actual formalization, also because of IP stuff. So it's always a bit hard to show you the insights of that. But that is just one example of the kinds of things that we're proving. We're proving that money doesn't just vanish in circulation. And this is this very abstract graph model, but we also have models of the actual wallet implementation. So the wallets are kind of software, hardware containers for those tokens, and they do end-to-end payments. So I can instruct my wallet to make a payment to someone else, and then we prove that those high-level wallet protocols work, so that the wallets can always retry and abort transfer and these kinds of things. And for that, we don't just use Isabel, we also use TLA+. TLA+ is not verification per se, it's model checking, but TLA+ is very good at modeling distributed protocols or distributed systems. So it was a lot easier for us to model how those wallets actually behave in the wild. Right. And I mean, we're one company doing that, but it's not just us. So there's a whole lot of other tech companies, and you might have heard of them, probably, so Google or AWS. I think some of you may have heard of them, who are doing that sort of thing. And the AWS team, I think they're routinely blogging about what they're doing. There's a fifth company here, where I couldn't find anything online. So the fifth company is Apple. And I only know it because I have a friend at Apple. And last year, when I met him for the Christmas celebrations at our former research lab, he said, oh, he's so happy because after years and years of fighting, they managed to convince their management to put a half sentence on their work in the annual report of Apple to their shareholders. So there's like many people at Apple working on formal verification for many years, and all they got is a half sentence in their yearly shareholder report. But they're very secretive about it, what they're doing. But basically, as far as I understand, they have verification about the security chips, the crypto chips that sit inside the MacBooks. So yeah, there's a few companies that are putting money into that sort of thing. And as the last topic for this presentation, I also want to suggest a new way of developing things, which I call proof-driven development. I'm not sure if anyone else is calling that, but I'm calling it that. And this basically goes back to this software engineering workflow that I showed you earlier, right? We're trying to shift our attention a bit towards the former phases. Because I believe that if we find conceptual problems before we implement them, then it manifests as fewer bugs. Obviously, it also means that we have a longer time to market, but in some industries, time to market is not so important than, like, you know, not losing money or not killing people or, like, you know, not doing harm to someone. And I have some specific examples about that. So we have implemented a batching procedure where the backend system that verifies requests that come in from the wallets has been made more efficient by just bundling multiple commands in one database operation. So one thing, how you could imagine that, is having a one-to-many payment, right? So if an employer sends out salary payments to all of their employees, it's typically coming from one account going to multiple accounts. So this is very inefficient in the old system, and in our system it can be made more efficient by batching all of this together. Another thing is that we have done in that way is garbage collection. So actually pruning the old state space from the database, the stuff that we don't need anymore, the tokens that have long been spent, just like removing them. And the third example would be offline payments. So actually touching your phone or some other kind of wallet device on the point of sales terminal and then being able to complete this payment without any online connectivity. And basically, if we draw the circle again, I would call like these initial 3 steps the PDD, the proof-driven development. And the question that we're asking ourselves is when we're doing that is, can the feature work correctly? Are there any undesirable feature interactions? And how can we then implement the feature, right? And we have explored this in multiple cases with the ones that I mentioned, for example, with Isabelle or TLA Plus before we actually started writing a single line of code. And it was worth it because in some of these things, for example, the garbage collection, we found a flaw in the initial design. And we could fix that flaw before it ever had the chance of even going to production, right? So it would not have, like, no customer would have ever seen that bug because we fixed it initially. And to some extent, it's a bit harder to sell that to the product people in the company because they want to see a prototype, they want to see something that's tested out. But if I then get back to them and saying, you know, everyone was so convinced that this is going to work, and then we typed it into Isabelle and showed us some counter examples, you know, that was a reckoning. And then we can say, well, we have a good argument that we will do that in the future because, yeah, you know, sometimes we just don't see those problems, and we wouldn't even see them in testing. We would just see them if we actually try to prove that it's working correctly. Now, there's a whole lot more things I could talk about, a whole lot more that we have on the roadmap. One of the problems that we have is that we are using Go as an implementation language, and Isabelle currently does not support Go as a compiler target language. So Isabelle, if you program something in Isabelle, you can generate it to Scala and to Haskell and to a few other languages. It didn't used to support Go, but now we have a completed master thesis that's gonna come out very soon, probably be included in the next Isabelle major release, where we can actually generate Go code from Isabelle. So we don't need to compare our handwritten Go code with the Isabelle code and see if there's some mismatch. We can actually push a button in Isabelle and say, please generate that Go code. And you know, there's many things that we could be doing more. You can always have more coverage. You can always use, you can get closer to the actual implementation. There's always going to be some gaps here. So one of the gaps that will probably stay forever is that those smart cards or secure elements that are in the phones, those tiny chips that keep those tokens safe, they are programmed in a very funny dialect of Java. So I'm not sure who here has heard of Java card. Java card pretends that it's Java, but it's actually a very different semantics. And I think this is probably going to stay a gap forever unless we can find some research money for 3 PhD students to write a formalized semantics of Java card. Yeah, so this is one of the things that I would love to do if I had infinite amount of time. But yeah, anyway, this is basically just an experience report of that we're doing this. It works well for us, but there's always more to do. And I guess with that, thanks, and open for questions.
Okay, I think we'll have time for 1 or 2 questions.
Great, thanks. Hello, I'm Simon Peyton-Jones. One of the things that's difficult about formal methods is scale. So if you've got a 500,000 line financial program, it's quite hard to verify every aspect of it. So, but you're talking about something that's deployed in practice. So I'm intrigued about how you deal with the problem of scale.
Yeah, we have to prioritize, plain and simple. So we do not have our entire stack formally verified. We have the core of the system that processes transactions, and then we're trying to move outward from there. However, people generally write code faster than we can verify the code, and we're just like 3 people in the group who are working on that, and not even full time. So I can confidently say we have not solved the problem of scale. We just have to prioritize and like look where the most expensive bugs could be hidden.
How big is the core?
How big is the core? That's a difficult question to answer because I have not been implementing it anything like in the past 2 years. Just working on the formal methods and PowerPoint basically. I would guess maybe 5 figures, or like low 5 figures, something around that, 10,000, 20,000 lines, probably.
So I do a lot of testing nowadays, and I enjoy it. So let me put on a devil's advocate hat a little bit and ask you about the examples you showed us at the beginning of the talk. So you talked about the bug in binary search, which was caused by integer overflow. So it's easy to think that if only Java integers were big nums, that bug could not have happened. And if we think about the bug in Tim's sort, if I remember correctly, that was there because there was a stack that was represented as a fixed size array, and it was not large enough in the Java implementation. And it's easy to think that if only they had used a dynamic data structure there, then that bug could not have happened. So that's a bit of a common theme, that there is something called the small scope hypothesis that hypothesizes that most bugs can be provoked by a small counterexample. And that is broken by things like 32-bit integers or fixed size arrays. So maybe a different way of approaching the problem would be to say, let's avoid those features in programs and in programming languages that make testing work badly. And how big a part of the problem do you think one could solve by choosing big nums, dynamic data structures, and so on, just avoiding these situations where overflow of one sort or another can cause a problem?
Yeah, I mean, that's a very good point. And we see that already in when we use Go as our implementation language, because Go has certain programming patterns that are even called best practices that are kind of error-prone. And you could say that if only we would be using them correctly, if only we were holding it wrong, then it would be a lot better to solve. But there will always be semantics problems that you cannot find by that you cannot prevent from happening by these best practices, right? So one of the problems that we found here was some subtle duplication of events happening. So you could have like just resend the same command, and then it would do something that was not expected. And the fix was not just slapping a timestamp on it, but it was something that had to do with like actually checking the semantic duplication of that command. And I think best practice would not have solved that from happening. But I mean, you can get a long way. This is why I showed this paper, like, simple testing can prevent many critical flaws.
Okay, I'm afraid we won't have much time for further questions. Let's give another round of applause to Lars.